Good morning, afternoon, evening, wherever you are. This is the third one in topic 10, so 10C if you like. We spoke about parallel plates last time. I just want to go a bit further with that. So, parallel plates is a region where we get pretty much uniform or constant electric field, and that becomes very useful. So if I apply a voltage, a potential difference, whatever that voltage is, a voltage or a potential difference, same thing, it's a difference in potential. And so with the diagram here, that's showing that's the positive side, that's the negative side, and it's an unknown number of cells in between. Normally when I've got it like that, we talk about that as a battery. Technically that's a cell, and then a combination of several of them. Is a battery, and sometimes it's shown as dot dot dot, saying, well, we're not sure how many bits there are, but it's just sometimes that symbol is used to stand for a battery. Battery, literally a whole stack next to each other, like battery hens that are all in cells next to each other. Okay, so I've got a separation here of D. The electric field, really common question to draw the electric field lines between parallel plates. I can arrange this, I can have the plates like that, or whatever. So this is the positive terminal, so we'll have our positive plate here and therefore our negative plate here. And the electric field, the direction of the electric field is the direction of the force on a positive charge, away from positive towards negative. If you put a positive charge in here, it would be pushed away from the positive and pulled towards the negative. So the direction of the electric field is vertically up. Okay? So there's my mark for getting the electric field in the right direction. But the electric field looks more than that. It's a whole series of lines. Remember that the magnitude of the electric field is greatest when the field lines are closest together and weakest when the field lines are far apart. Field lines are close to, the field is uniform here, so the field lines are going to be equally spaced. So let's just put that there. Try to make them equally spaced. I haven't measured them, ruled them or anything. Oops, that's got a bit close. And then at the end where it's spread out, put those two a bit close together, but hopefully not enough to lose a mark on that. And I haven't drawn that one very well, but something like that. So the arrows all in the same direction. So 3 marks often for this question. 1, that you've got the arrow in the right direction. 2, that you've got these lines equally spaced. And 3, that you've got them bulging out at the end. Here there's a certain concentration of lines. Here the lines are not so close together, so the field is weaker. Well, of course they are, because there's no parallel plates adding to them out here. So at the end, you've got the end effect or the edge effect of the parallel plates. Okay, so what formulae do we know? Between parallel plates, E is equal to V over D. So it's measured in volts per metre. But we also know is that electric field is F over Q, so it's measured in Newton per Coulomb. And they are equivalent units. Volt per metre is the same as Newton per Coulomb. And we can measure, probably between parallel plates, we normally talk about in volts per metre. Around a point charge or something, we normally talk about in Newton per Coulomb, but technically either of those is correct. We also know that EP is equal to, we know that V is equal to EP on Q, and therefore EP equals Q times V, or delta EP equals Q times delta V. That's a pretty important one actually, and for this one here I can get that F is equal to Q times E. Alright? So we've got all those formulas, and even though these are just from the definition of electric field, from the definition of electric potential, you know, probably these ones you're going to be using more often. Okay, so where we use these parallel plates, it's a bit like a projectile motion thing, you know, at or near the surface of the Earth, the gravitational field is pretty constant, right? Between here and a kilometre up, you know, there's virtually no change in the gravitational field, 9.81 Newton per kilogram or metres per second squared. Note that there's 2 units for that. Gravitational field in Newton per kilogram or in metres per second squared. The acceleration due to gravity is in metres per second squared. But Newton per kilogram is an equivalent unit to metres per second squared, just like volt per metre is an equivalent unit to Newton per coulomb. If I throw a stone horizontally off a cliff, it follows a parabolic path because there's a force acting on it. The force is always constant and in the one direction. If I throw something up, it goes up and stops and comes back down. Same thing's going to happen between parallel plates. So, let's stick to the same situation we've got here. So the electric field again is directed up. I'll spread them out a bit so they're not taking up so much space there, so I've still got room to write on things. And when you're drawing this, so in this question it hasn't asked me to draw the electric field, so I haven't sort of drawn in the edge, but it's just to remind us which way things are going. Right, let's use a different colour. So we use let's use a nice green pen. Do they work? A couple here, surely will work. Okay, if I fire a proton in, then the proton, I'll call it a PHYS. I mean, we could technically have a P minus an antiproton, but if I fire a proton in there, then as it heads in here, it will experience a force. It will experience a force because it's a positive particle. The direction of the electric field indicates the direction of the force on a positive charge. And, you know, a proton is a positive charge. So it'll experience a force in the same direction as the field, i.e. up. Now, you know, just like when I throw a stone horizontally, there is no force in the horizontal direction, so the horizontal velocity remains constant, but the vertical velocity, which was initially 0 when I throw that stone off the cliff, gets bigger and bigger because there's a force in that direction. In this case, it's going to be bent upwards in a parabolic path. Right. So, in the horizontal direction, and of course I can complicate things by having the plates up like that, in which case going through the middle it's going to bend, you know, to the left or right. And so in this one here we're firing in horizontally, there's no force, so no acceleration. In vertical direction, F equals, just like F equals m times g for the gravitational force acting on an object, F equals q times e. Again, so you see here, it's these, you know, ones here that become, you know, more significant. But E is equal to, well, V over D. Okay, F equals equals Q times V on D. A equals F on M, which is Q times V over M times D. So we get that acceleration in the vertical direction. The path will be parabolic. And probably it's only going to bend a little bit, you know, it depends on how strong the field is. In the same situation, same, it doesn't have to be the same. I mean, often they'll give you a question and say, what's the polarity of the battery? Which end is positive and which end is negative? If the proton goes up, or if the proton goes down, or if the electron goes up, or the electron goes down. Let's have two particles coming in here. Let's have an electron minus and a neutron. Okay, so I'll just draw in those same field lines. So the field is still like that, we haven't changed. So positive display, the field is from positive to negative, away from positive. Okay. So what happens to the electron? The electron comes in and it's going to be deflected, you know, and you know, it's sort of when you throw a stone off a cliff, of course it falls downwards because that's the direction of the force. If you threw a stone off a cliff and it moved in a parabolic path going up, that would be pretty weird. Well, in this one, because of the electric force, you know, it could be bent one way or another. We could be looking from above, and it could be bent left or it could be bent right. In this case, to bend up seems strange, but absolutely possible. That's what happened to the proton. The electron will get bent down, right, in the opposite direction. So the electron gets bent down. We draw that again. Easy to say. In terms of how it gets bent down, if everything else is the same, and it may not be, you know, we might be travelling at a bigger speed. Certainly the charge on an electron is the same as the charge on a proton, so therefore the force would be the same. But the acceleration on the electron will be much, much, much greater. Remember, the acceleration is about nearly 1,800 times less massive than the proton, and so it'll be affected a lot more. So let's just draw that a bit sharper. I'll draw it in green, I suppose, just stick with the convention that I used. So the electron comes in and bends. Again, probably should be a lot sharper now, or maybe the proton wouldn't even, you know, come out, wouldn't even hit the plate. And the neutron, what happens to the neutron? Charge on a neutron, 0. Therefore, the electric force on the neutron, 0. The neutron, go straight ahead. Alright. And so, if we had, for example, let's just move the plates around a bit. So I'm going to have plates going like this, and I'm going to have some radiation. I'm going to have alpha, beta, and gamma radiation coming up here, and that's enough information, so I want us to draw the paths of each of them. So again, positive side here, so the electric field is in this direction. Alright? So the direction, you know, I could label the plates, positive plates here, negative plates here. So an alpha particle to start with is much more, has a mass of 4 protons and neutrons. So 4 lots of 1800 is about 7,200 times more massive than an electron. The alpha is going to be pushed away from the positive and towards the negative. It's going to go in the direction of the electric field. So the alpha is going to be bent that direction. But before we do that, the beta is going to be bent towards there. So get rid of that field line. Beta is going to get bent like that, okay, in a parabolic path. Alpha is going to be bent, but so let's just have a think, so force of alpha on force of beta. Which one will experience the greater force? We've got to take it back a step. Q alpha on Q beta. Let's find the magnitude of that. An alpha particle's got 2 protons and 2 neutrons. Remember that from when we did the radioactivity. And so it's got twice as much charge. F is equal to QE. They're both going into the same field, so it's got twice as much force. So it's a bit like and I think we probably use an analogy a bit like this when we were talking about the alpha beta radiation. So a truck going past and 2 people push that sideways, a cement truck. 2 people try and push that. Not going to have much effect. A bicycle going past and 1 person pushes that will deflect that a lot. So even though the alpha has twice as much force, the beta is going to have a much bigger acceleration. So acceleration of alpha on acceleration of beta, I think it'll be 2 over 7,200, so I think it's going to be 1 over 3,600, something like that. So what's going to happen is that the alpha is not going to be deflected much at all. So here's the beta coming out here. Alpha hardly deflected, and I wanted this like that, so it's deflected a bit. Alright? What happens once it leaves the field? Does it go back to the direction it was travelling? Does it keep on bending around? Or does it go in a straight line like that? Once it's left the region of electric field, there's no longer a force acting on it, so there's no longer an acceleration, so it no longer bends. And so it'll keep going in a straight line there. So it doesn't keep on bending, so it's not like that, like a parabola. It certainly doesn't go back to the angle that it was going on. It keeps on going in a straight line. I've seen that question a few times before, so and particularly so with magnetic fields, when when a particle leaves the region of magnetic field, which is something later on. Okay, and the gamma, of course, so this one is the alpha, the gamma. It goes straight through undeflected. In many cases, let's move back over here. In many cases, we're using the parallel plates not to bend or deflect electrons, but to accelerate them. And so if I have an electron coming into the region between parallel plates, it will be accelerated across through here, it can shoot through here, and it's just like dropping a stone, a brick, and it accelerates as it goes through. And so, again, the direction of the electric field in this case, I think I've drawn the field in red most times. So the field is away from positive and towards negative. I haven't drawn in the end effect, and I'm not too worried about just having them equally spaced there. Christian hasn't asked that, I'm just using that to show this. So it looks like the electron's trying to go uphill. When you draw the field lines, make sure that they're all the way to the plates there. Again, that's just a bit fussy. I think mine are okay there. And so the electron coming in is, it looks like it's going against the field, and it is, because it's a negative particle. So the direction of the force on the electron is in that direction. Okay, so in this case, delta EP equals Q times delta V. So as it goes from here to here, it's like the brick going from the roof down to the ground. It loses gravitational potential energy and gains kinetic energy. So let's go from A to B as the electron goes from A to B, it loses electrical EP and gains EK. EK gains Q delta V. Gains 1.6 by 10 to the minus 19 times 20 equals 3.2 by 10 to the negative 18 joules, or 20 electron volts. Alpha particle. 5,000 volts. And of course, an alpha particle coming in here would be slowed down, just like throwing that same brick up in the air. It would gain potential energy and lose kinetic energy. It's going the opposite direction of the force. But so an alpha particle, if we have the polarity change, it would gain. The charge on an alpha particle is 2 by 1.6 by 10 to the minus 19. That's the charge times delta V is 5,000 equals 8,000, 16,000, 1.6, 10 to the minus 16 joules, I think, or an electron would gain or lose 5,000 electron volts, a proton would gain or lose 5,000 electron volts. An alpha particle, since it's got a charge of 2, would be 2 times 5,000 equals 10,000 electron volts, or 10 keV if you like. The rest, we've already answered the question. So the last bit of that exercise before we move on to the gravitational spacecraft one, which is interesting. Oops, I think I'm out of shot here. You don't need to see me, as long as you see him. The last bit there is talking about combinations of fields and potentials. So fields, of course, are vector quantities, and so if we've got a combination of fields, we need to add them vectorially. Potential is a scalar quantity, so when we add those, we add them taking into account their sign. So if you've got 2 charges and we talk about a point here, what's the potential due to this one? What's the potential due to that one? The overall potential will be the sum of those. And if it was plus 10 volts and plus 3 volts, then it would be plus 13 volts. But if it was plus 10 volts from one and minus 3 volts from the other one, then it would be plus 7 volts altogether. So it's not the direction, but we're still taking into account whether it's a positive or negative potential. Okay. I think the next section is a big one where we're looking at satellites and so on. So I'll start a new video for that one.